So now we have seen that xk is the formula for DFT. So in this formula, you can find out that xk is calculated as a summation for n is equal to 0 to n minus 1. So if I first tell you that it's a 4-point DFT, that means it's a summation from n is equal to 0 up to 4 minus 1, that is 3. So x4, that means if you're trying to find out the DFT for 4-point DFT, every term, that is x0, x1, x2, x3, mind it, it is a small x, it should be capital X. So every term should be addition of 0 to 3, that means 4 terms. Okay, so to finding DFT or IDFT, every term will be addition of 4 different terms. And there is a very important concept which is called as Tweedle factor. So this DFT to FFT, what is the need of DFT? I told you so far, that is converting a discrete sequence into from time domain to frequency domain, because frequency domain gives some specific features. Now, conversion of time domain to frequency domain is done by DFT. Same thing is done by FFT as well. And DFT result, FFT result, DFT spectrum, FFT spectrum, all are same. Then the question is, why FFT? Okay, we'll find that FFT is nothing but a easier version of DFT. That is, DFT is time consuming, DFT is computationally not that efficient. That means too many calculations have to be done in DFT. But it is a very effective technique, but computation efficiency is not there. So the technique is efficient, but the method is inefficient. That is DFT. What we can do in FFT is we can keep the efficiency of the we can keep the technique, okay, intact. That is, FFT also will be converting time domain sequence into frequency domain sequence, but in a more smarter method, that is with a lot less number of computations. And the whole thing is done by using the periodicity property of this Tweedle factor. Okay, so that's why this Tweedle factor, which is nothing but e raised to minus j 2 pi by n. So n is nothing but uh, point, okay, number of point of DFT. So if I ask you calculate a 4-point DFT, in that case this capital N will be equal to 4. 8-point DFT, capital N will be equal to 8. Okay, so this Tweedle factor, we will find that it's having a periodicity property, and by using that, DFT algorithm has been made easier by Mr. Cooley and Tukey. Okay, these are two scientists who are the inventor of FFT, and we will see why FFT. But FFT and DFT, that way, result-wise, they are same. Method-wise, they are same. Technique-wise, they are same, but method-wise, they are different. This below is called as a DFT IDFT pair. That is, this is called as forward DFT, and check that this is capital X. Okay, this is very important. Whenever I am saying XN, that is time domain signal. That is small xn. Okay, but whenever I am saying DFT frequency domain signal, that will be called as capital XK. So remember all the transformed domain things. You do Laplace, you do Z, you do Fourier. All the transformed domains are given by means of capital. Okay, and this is actually again from DFT when you are coming back to IDFT. In that case, this is called as inverse DFT or IDFT. So here from time domain xn, you are going to frequency domain capital Xk. So input here is xn, time domain discrete sequence. Output here is frequency domain discrete sequence. So this is called forward DFT formula. FFT also we are going to use the same formula, and here frequency domain discrete things are given, sequence is given. From there I'll be doing IDFT, and I'll be getting again the time domain sequence discrete. Okay, so that's why this is first formula is called as forward DFT from small xn to capital Xk. Second formula is given by inverse DFT, so from capital Xk to again small xn. And if you check these two formulas, first difference is this Tweedle factor is using Kn as the power, and this Tweedle factor is using minus Kn as the power. Okay. Here there is no 1 by n, here there is 1 by n. Okay. So if there is a 4-point IDFT DFT you are calculating, in case of IDFT I have to divide the all the coefficients calculated by a factor of 4. 8-point DFT have to do 1 by 8. So these two are visible differences. Generally, there are three differences in DFT and IDFT. Two are visible from here. Another one is not visible from here, but that we will see in the FFT algorithm. That is actually called as bit reversal kind of a thing. That is, input we have to arrange in such certain way to get a correct output. Okay, so that also we will be seeing in case of IDFT algorithm. But this is more or less the DFT twin, it is called. Okay, so this is called DFT twin formula. So two formulas goes hand in hand, DFT and IDFT. It is like this. So what are the usage of DFT? So the DFT pair allows us to move between the time and frequency. So forward DFT formula take us from discrete time to discrete frequency domain, and inverse DFT takes us from discrete frequency again back to discrete time domain. So this actually helps us during by using whenever we are using DSP processors at that time, this DFT IDFT, this twin formula helps us a lot. Time domain sequence xn is discrete and has spacing of ts, where ts is the sampling time I told you. So xn, small xn, okay, so they are spaced in time, or they are quantized in time with a space of ts, that is sampling time. Whereas a frequency domain sequence xk, just check, this is capital Xk and this is small xn. This is time domain, frequency domain. So xk is discrete frequency domain thing. It's having a spacing of 1 by nt. So n is nothing but the point of DFT, 4.8 point, 16 point, likewise, and that point is actually given by power of 2. So if it is a radix 2 DFT, so this n can be 2 raised to 1, 2 raised to 2, 2 raised to 3, and accordingly. In our exam, the maximum ask up to 2 raised to 3. Nobody will ask you a 16-point DFT or 16-point FFT in exam. Okay. The maximum will ask you up to 8-point only. So this n for us maximum can be 8. Okay, and t is nothing but the time interval in digital, okay, or discrete. Let us now check an example. Already you know what is DFT, but then also I will do this thing in a faster manner. What we are supposed to do is here, so there's a sequence in time domain. So let us say this is spaced by some sampling interval ts. That is not important while calculating DFT. Only the sequence is important. So sequence is 1 2 3 4. Okay, and we are supposed to find out DFT. So this is the formula, capital xn, so this is small xn, and capital xn we are supposed to calculate. N is equal to 0 to n minus 1 xn wkn. Okay, now there will be 4 x. Okay, so there will be x0 for k is equal to 0. There will be x1 for k is equal to 1, x2 for k is equal to 2, and x3 for k is equal to 3. So from x0 to x3 you have to calculate, because n mentioned as 4. Calculate 4-point DFT. This is 1 2 3 4. If I give you this sequence and ask you to calculate radix 2 DFT for 3, that means 2 raised to 3, that means 8 point. Okay, is it possible? Answer is obviously possible. In that case, what you have to do is xn 1 2 3 4 is given, that is n raised to 0 to n raised to 3. Then you have to extend this thing by 0 padding. So here you have to add 4 zeros, and you have to make it n is equal to 1 to n is equal to 7. Okay, so 1 2 3 4 0 0 0 0, and then you can apply the same process and you can calculate in that case x0 up to x7. Okay, so any point I can give you, and I can ask you to find endpoint DFT of 4, endpoint DFT of 8. So if the input sequence is not having that length, you have to make it to that length by padding 0 at the end. Okay. So as you know DFT, as we have already done DFT, then I'm telling you all this thing. Okay, so first I'm supposed to find x40. Okay, somebody don't write 4, xn0 or xnk, somebody directly write x0. Okay, I'm writing x40 because this 4 indicates that the value of k. Okay, so that means here k is equal to 0 and n is equal to 4. So this 4 actually indicates the value of n, capital N, not k, I'm sorry. Okay, what how you are supposed to find out? So there's a formula, n is equal to 0 to n minus 1, that is 4 minus 1 3. So for all formulas it is n is equal to 0 to 3, xn wkn. Expand this. Okay, so xn is nothing but this input. So this is small x0, small x1, small x2, and small x3. So this is x0. So x0 is 1, x1 is 2, x2 is 3, and x3 is 4. And then you are supposed to write down w4 0 0, So here this is important thing I wanted to tell you. W4 0 0. So this 4 is nothing but n is equal to 4. It is given in red. What is the 0 0 means? The value of k and value of n. So what we are supposed to find out is k is equal to 0. We are asked to find x0. So that's why for all these four things k will be equal to 0. Okay, but n value will keep on increasing because here the n value is changing from 0 to 3. So for the first term in total factor k0 n0, second term total factor k0 n1, third term total factor k0 n2, and third term k0 n3. So I'll repeat, we are asked to find out xn of k, that is x4 of 0. So this 0 is nothing but the value of k. So k is there in total factor. So in total factor, there are three variables. One is capital N. I have asked you to calculate 4-point DFT. So capital N is equal to 4. And here k is equal to 0 and n is equal to 0. This is the first term. Second term k is equal to, so for all this, k always will be equal to 0 and n will keep on increasing from 0, 1, 2, 3. And then you expand. So what is meant by w400? So this will be x0 e raised to minus j2 pi 0 0. Okay, so here like this, and the first term here it's a mistake, this x0 should not be there. So this is x1 e raised to minus j2 pi 0 1 of 4. So here I have made k is equal to 0, n is equal to 1. For here x2 k is equal to 0, n is equal to 2, and here k is equal to 0 and n is equal to 3. So for all these cases, the values of e raised to something e raised to 0 will be equal to 1. That means if you go in the next slide, you'll find that uh, it is x0 e raised to minus j2 pi 0 0. That is k0 n0. This is k0 n1. This is k0 n2, and this is k0 n3. And this is x0 x1 x2 x3. So all this e raised to 0, that means will be 1. Again e raised to 0, 1, e raised to 0, 1. So this will be nothing but x4 0, that is x0 is nothing but 1 plus 2 plus 3 plus 4 is equal to 10. Okay. So whenever you are trying to find out x0 either for endpoint n is equal to 4 or n is equal to 8, directly add all the sequence. So 1 plus 2 plus 3 plus 4, if you are doing, you are getting 10. That will be the value of x0. And what does x0 give you? X0 is nothing but give you the DC component of DFT or strength of the signal. And this thing is having no frequency because this x0 you have calculated as the first component in frequency domain. First component is frequency domain means k is equal to 0. K is equal to 0 means no frequency or DC frequency. So if you're adding all the components of the xn signal, in that case what you are getting in the frequency domain is the DC component of the signal in frequency domain. Next will come capital X1, capital X2, and capital X3. So those three things are the frequency based component, and X0 is nothing but the DC component. Let us find out how to go for X1. Okay, so it is called X41. 4 is nothing but the value of capital N. So in this case again x0 e raised to, so previously this was 0 0 because k is equal to 0, n is equal to 0. Now as k is equal to 1, this has become 1 0. Now k is equal to 1, n is equal to 1, so this has become 1 1. K is equal to 1, n is equal to 2, so k value is not going to change for the whole row. K value is going to be constant, only n value is going to be changed. Okay, and k is equal to 1, n is equal to 3. Now this values you have to calculate what it becomes. So this is 0, that means first thing will be e raised to 0. Now this thing becomes e raised to minus j2 pi by n. This becomes the total factor, with that multiply 1 1. So this becomes e raised to minus j pi by 2. So this is the total factor. Okay, and there is a symmetry in the total factor, you will find. Okay, e raised to minus j pi. Okay, so minus j pi, you have to remember e raised to minus j pi is minus 1. We will see that. Okay, and here e raised to minus j2 pi into 3 by 4, that is e raised to minus j3 pi by 2. And if you calculate e raised to minus j pi by 2, that means cos pi by 2 minus j sine pi by 2. And cos pi by 2 is 0, sine pi by 2 is 1. That means this will be giving you the value as minus j, which is given here. What is here? Cos pi minus j sine pi. So cos pi is minus 1, which is given here, and sine pi is 0. Here this is cos minus 3 pi by 2 and minus j sine e raised to minus j3 pi by 2. So this is cos 3 pi by 2 minus j sine 3 pi by 2. So that will be equal to plus j. Okay. And now if you're just doing all these calculations, you're going to get minus 2 plus 2j. Okay, so this is the x1 or capital X1, or this is the first frequency component with k is equal to 1. Okay, now in the same way find x2. Okay, in that case k value will be 2, so you can check here the same thing. So x0 is 1, x1 is 2, x2 is 3, and x3 is 4. These things are not going to change. What will change is the total factor. And if you are changing the total factor, k will be equal to, so e raised to minus j 2 pi by 4. This is actually total factor. E raised to minus j 2 pi by 4, that is e raised to minus j 2 pi by n, that is the total factor, multiplied with k and n. K and n keeps on changing. So here I am asked you to find out x2, so k will be equal to 2, and n is equal to 0, n is equal to 1, n is equal to 2, and n is equal to 3. And then what you'll find is you'll be finding this is e raised to minus j pi, e raised to minus j 2 pi, e raised to, so accordingly so the pi factor is missing here. I'm sorry, I'll just change it. So finally what you will find is this is nothing but minus 2. So for example, how did you calculate x0? Just by adding this thing 1 plus 2 plus 3 plus 4. And if you're finding this is the middle part. Okay, how to find the middle part? So x0, leave that x0, then whatever is remaining x1, x2, x3, whatever is the middle component of that, that has to be calculated by 1 minus 2 plus 3 minus 4. If you are doing a 8-point DFT, in that case, zeroth part if you remove, that means first, second, third, fourth, fifth, sixth, seventh. So after, if you are removing x0, then x1, x2, x3, x4. So x4 is nothing but the middle term. So that x4, how do you calculate? Whatever is given, you just keep on doing it, plus minus, plus minus, plus minus, and just do a very simple addition. Okay, we will show that during the final thing. Okay, so here it is coming to be 1 minus 2 plus 3 minus 4. Okay, because 1 2 3 4 is given as the sequence, and then x4 is calculated by 1 minus 2 plus 3 minus 4. So this total factors are doing this game. So total factor is a very funny and very periodic kind of a thing, and it is having a very nice property of symmetry. Okay, so how to find the middle term? So middle term for 4 length DFT is nothing but x2. Okay, so x0, x1, x2. So how to find x2? 1 minus second term plus third term minus fourth term. If you this you do, you are getting minus 2. And in the same way, how to find x4 3 or x3? In that case, k will be equal to 3. So in this case, k is equal to 0, n is equal to 3. You are finding this. Then accordingly, so you'll be finding j minus j and this. So you are going to get as x4 3 is minus 2 minus 2j. So 4-point DFT for the length 4 signal xn 1 2 3 4. So in frequency domain it will be xk. So just see that this small xn and this capital xk, and the DFT is nothing but 10 minus 2 plus 2j minus 2 and minus 2 minus 2j. How did we find that first term? Just by adding all the xn things. So 1 2 3 4 was given, 1 plus 2 plus 3 plus 4, that is equal to x0. Okay, so you won't have to calculate by any method. For sequence 7 or for sequence 8 also you can do that. Just add all the terms, you will be getting x0. How to find the midterm here? 1 minus 2 plus 3 minus 4. Okay, that way you are going to get what is called as x2, and then calculate x1 properly. Okay, this is minus 2 plus 2j. If you are calculating this properly, no need to calculate x3, because x3 will always be the complex conjugate of x2, oh sorry, x1. Okay, so as x1 is minus 2 plus 2j, you do anything, x3 will be minus 2 minus 2j. That is, x3 will be always a complex conjugate of x1. So actually, if you are looking at DFT, 4-point DFT, 4 things you have to calculate. First thing, just addition of all whatever is given. Third thing, alternate plus minus, a plus minus you do, and just do very simple addition, subtraction. You are getting the third term. Second term, how can you get it? It is nothing but only one thing you have to remember how to get it. So this you have to calculate by this formula. So this is given how to calculate 1. So you have to remember these total factors. So first term is multiplied by 1, second term is multiplied by minus j, third is minus 1, and fourth is plus j. And the last term is nothing but complex conjugate of the second term. So whatever I'm showing in the previous 3-4 slides, such a big explanation and all those things I'm giving, it can be put only in one very simple matrix form. Okay, so xk we are supposed to find out, that is the frequency domain 4-point dft, or fft also will be having the same result. This is actually called 4-point twiddle factor matrix. And this, if you remember, just multiply the given any sequence and directly you'll be getting what is the DFT or FFT. How to remember this? So in this case, n is equal to 0, k is equal to 0. In this case, k is equal to 0, n is equal to 1, k is equal to 0, n is equal to 2, k is equal to 0, n is equal to 3. So for all the first row, the value of k is 0. Hence the twiddle factor become all 1. And for all the first column, the n value will be equal to 0. Hence the twiddle factor will be all 1. So there are 16 elements. There are 16 elements here. How to remember the 16 elements? So all the first row and first column element becomes 1. That is the first thing. And remaining is 9 elements. Okay. So all the first row, first column element becomes 1. So that becomes 7. So all 7 elements are 1. And in this 9, central element is again 1. Okay, so first all the first row, first column, done. It's all 1. Then remains a 3 by 3 matrix. Then remain a 3 by 3 matrix. In this 3 by 3 matrix, what we have to do is the center of the 3 by 3 matrix we have to write as 1. And up -1, left side -1, below -1, and left side -1. So out of the 16 components, 12 components are not complex. So out of the 16 components, 12 components are very simple. Complex means with j, okay, complex term, that is a plus jb. So out of this 16 terms, 12 terms are not complex. Only 4 terms are complex. So only one thing you have to remember in this whole matrix, that is position of second row and second column. This is -j. This is the only thing you have to remember. So how to write it? All this 4 and this 3. So all this 8 to 7 components are plus, and remaining there is a 3 by 3 matrix. Center of that is also +1. Okay, these are 8 components. And then above you go, and this is -1, right side -1, left below -1, and left side -1. So these are all real components. Not, there is no imaginary term. And then in imaginary, second row, second column is -j. And this is complex conjugate of -j, that is j, and below is complex conjugate of -j, that is plus j, and this is actually complex conjugate of j minus j. So this four corners are actually complex conjugate, and this one position you have to remember. For forward dft, this thing is going to be -j, and for inverse dft, this is going to be plus j. Remaining all positions are the same. So this is going to be j for inverse dft, this is going to be -j, this is going to be j, and again this is going to be -j. So this is the change in position of twiddle factor that is there in case of inverse dft. We can see that later on, but for forward dft you have to remember that is the 7 positions, all the first row, first column elements are going to be +1, and third row, third column is going to be +1, and all the above, side, below, and left side elements are going to be -1. Second row, second column is going to be -j, and second row, fourth column will be plus j. Fourth row, second column will be plus j. Fourth row, fourth column will be -j. And if you just do this multiplication, you are going to get the same result: 10 minus 2 plus 2j, -2, and -2 minus 2j. So this was one example which was asked in your exam. Okay, that's how you are solving it. Same thing given as 2, 2, 3, 1. So if it asks for 8 or 10 marks, in that case you have to do it in this fashion, that you have to write the whole formula. Be careful, I have written this x0 by mistake, so this should be x1 into e raised to minus this. I'll correct it while I send you the PPT. So if it is asked for 8 or 10 marks, in that case you have to do this thing in elaborate manner. But if it is asked for 5 marks, in that case just write this 4 by 4 matrix and multiply this equation by x0, x1, x2, x3. So these are small x, that means this is time domain thing, and these are all capital xk, x0, x1, x2, x3, that is this part x0, x1. So these are all frequency domain thing. So never write the result of DFT or frequency domain things in small letters. Okay, never make that mistake. Okay, so these are all to be capital letters. So here what we are going to do is how the DFT look like. That is the question. Okay, whatever things we are finding, so we have found the DFT like this, but we have to draw the spectra for this. That is how the DFT look like. And whenever you will be doing FFT based spectral analysis, image analysis, there you have to show the whole image, or maybe any kind of input signal into spectra form. Okay, so how to do that, that we are going to find out. So we have done the same thing, that is we have written this 4-point DFT. So this is the algorithm, or this is the Tweedle factor matrix. So this is the Tweedle factor matrix, or there is the transform matrix. In that case, multiply 2 2 3 1. So don't make mistake here. So this is x0, small x1, small x2, and small x3. Write like this: 2 2 3 1. And how to write this matrix? Final time I'm telling you, all the first row, all the first column elements are 1. Then there remains a 3 by 3 matrix here. Central element is 1. Top, left, bottom, and right are -1. So these are the 12 components which are real. And second row, second column is -j. And all the remaining positions are complex conjugate. That is, second row fourth column is +j, fourth row second column is +j, fourth row fourth column is -j. And if you are doing this multiplication for 2 2 3 1, you are going to get 8. So you added 2 plus 2 plus 3 plus 1, that is 8. So there is a DC component in the DFT result. Okay. How to find the central component? So you remove this. This is not a part of spectra, or this is actually a DC component. There is not frequency. There will be 3 more frequency components. So how to find the central of the remaining 3 more frequency components? So this is 2 minus 2 plus 3 minus 1. Okay, so alternate plus minus, 2 minus 2 plus 3 minus 1. So that will be 2. This is here. So here you can see this. Okay, 1 minus 1 plus 1 minus 1. That means 2 minus 2 plus 3 minus 1. That gives you 2. So this Tweedle factor matrix is nothing but the way the Tweedle factors are arranged in the previous in detail, the first principle, whatever rules I have shown you. So this is called first principle rule. Okay, whatever Tweedle factor matrix, the way they are appearing, that we have put in a matrix form. So that is this matrix. And if you are doing multiplication of this matrix with the input signal, you are getting this one. Now how to draw the spectrum? So while drawing the spectrum, you have to plot for amplitude. So this for k is equal to 0, that is a DC part. Check the amplitude. So this is the amplitude plot. For k is equal to 0, amplitude is 8. Then -1 minus j. Okay, how much is the amplitude? Root under of -1 square plus -1 square. So amplitude will be √2. So that's why x1 is having √2. So x-axis is k. This is very important. Okay, so the x-axis is k. So this is the first frequency component, that is a baseband frequency component. This is having amplitude of √2. Then there is k is equal to 2, that is the second harmonic. Okay, what is the amplitude? This is 2, so this amplitude also will be 2. Okay, so root under of 2 square, that is 2. And this is -1 plus j. Again, how much will be the amplitude? Amplitude will be root under of -1 square plus 1 square, that will be √2. So if you check at this amplitude plot, this should be a symmetric plot. So amplitude plot should always be a symmetric plot. You can check whether your calculation is correct or not just by finding its amplitude plot. And this thing should be complex conjugate, and whenever they are complex conjugate, they're same in phase, and they are same in amplitude and opposite in phase. Okay, so -1 minus j and -1 plus j, they are having same amplitude of √2, and they are having opposite phase. Okay, if these components are coming like this, then your calculation is correct, and if their amplitude is coming to be different, that means your calculation is wrong. You have to check it. Okay, only and this first and central component calculation is very easy. First component is to be calculated just by adding the given sequence, and the central component is found out just by 1 minus and 1 plus. Likewise, you keep on doing 1 minus minus plus you do, and you will be finding the central component. Now how to find the phase plot? So phase plot is 8 and 2, so they are real part, so they're having phase as 0 and 0. Okay, so 8 and 2 are they are having phase and 0 and 0. -1 minus j. So this is the way you calculated tan inverse imaginary by real. If you are doing that, it will be a mistake. because -1 - j is something which is falling in the third quadrant. So -1 - j means you have to come to the left by for -1 unit, and then you have to come below. So -1 means left and below. -1 plus j means left and up. So -1 plus j is a second quadrant thing, and -1 - j is a third quadrant thing. And whenever it's a third quadrant thing, it cannot be of angle 45, because 45° is appearing in first quadrant. So -1 - j will be angle of 180 plus 45. 180 is coming because you can take minus outside and minus of 1 plus j. Because of this minus, it will be out of phase 180°, and 1 plus j will be having angle of 45°. So it will be minus of 180 plus minus 45. So it will be kind of a 225°. Yeah, so this is what is 225° that we have plotted. So first plot this point, and then anti-clockwise from x-axis you can calculate, and you can find out how much is going to be the phase angle of -1 - j. Be careful, tan inverse of imaginary by real does not hold every time. Where is -1 plus j? Again, it is having angle of 45° minus, so it will be either you can write minus 225° or you can write plus 135°. So -1 plus j. So it will be having angle like this. So it will be having angle of 135°, and 135° is nothing but minus 225°. So one very important thing, that any Fourier things you'll be finding all the amplitude plots are even. Okay, this is even by leaving this k0 component. K0 is not coming in the spectrum. So spectrum is the frequency spectrum, which starts from k is equal to 1. Okay, so from k is equal to 1. So if you are plotting 8-point DFT, so k is equal to 1, 2, 3, 4, 5, 6, 7. So this 1, 2, 3, 4, 5, 6, 7 will be symmetric. That means k is equal to 4 will be the central component in that case. 3 and 5 will be having same amplitude. 2 and 6 will be having same amplitude. 1 and 7 will be having same amplitude. As you have done DFT, you know that x1 and x7 they are complex conjugates. X2 and x6 they are complex conjugate. X3 and x5 they are complex conjugate. Okay, so for 7-point 1, 2, 3, 4, 5, 6, 7 there will be a even spectra by keeping x4 at the center, and for 4-point x2 k x1 x2 and x3 will be a uh, even a spectra by keeping x2 at the center, and this will be an odd spectra. What is meant by odd? Amplitude same but phase difference and phase exactly opposite. So you are finding that phase of x1 is 225° and phase of x3 is minus 225°. So plus 135 can be said as minus 225. So very small calculations. You can take a pen and paper, you can plot all these points in the 4 quadrants, and you can check how this thing comes to be 135°, and how it is 135 is same as minus 225. So this is the how the DFT look like. I don't think anybody shows you this. You just calculate it, but you don't know how the spectra look like. And x-axis, be very careful. K is equal to 0, k is equal to 1, k is equal to 2, and k is equal to 3. The real terms 2 and 8, they should be having phase of 0 or no phase. Now there, we will start with FFT with all the background. So for n-point DFT, there will be n square multiplication and n into n minus 1 addition. If it is 4-point DFT, just I have shown you this kind of thing. So how many multiplications are there in every line? So x0 is multiplied with this, x1 is multiplied with this, x2 is multiplied with this, and x3 is multiplied with this. So there are actually 4 multiplications in every line, and such 4 lines are there. That means there are 16 multiplications in case of DFT. And how many additions? Every line there are 3 positive signs. So 3 positive signs means every line there are 3 addition, and every line there are 4 multiplications. So for 4 lines, that means capital X0, capital X1, capital X2, and capital X3, there will be total 12 addition and 16 multiplication. That is what is shown here. Example of 4-point DFT, each line has 3 addition sign and 4 multiplication sign. That means there will be 16 multiplication, that is n square, and 12 addition, that is 4 into 4 minus 1. Okay, if it is 7-point DFT, in 7-point DFT, there will be, sorry, 8-point DFT. In that case, it will be 64 multiplications and 8 into 7, that is 56 additions. Okay, so addition is a little less, but multiplication is directly n square, where n is the number of point of DFT. So advantage with FFT is, so if it is 4 point, 8 point, 16 point, in that case, you are finding it is small. But if I give you a sequence, speech sequence of 3 minutes, okay, and you have sampled it for 1 millisecond, just imagine how many input points will be there. And if I ask you to calculate maybe 1024 point DFT of that, so how many number of multiplications will be there? It is 1024 square. Okay, how many number of additions will be there? It is 1024 into 1023. Okay, so those things in DFT are avoided in FFT. And what is the efficiency increment in FFT compared to DFT? We have done the numerical for that. That also I will show you. Okay, so what is the advantage with FFT? Why FFT? First thing is lot less calculation than DFT. This is the one and only reason. So by FFT, the same DFT result is obtained, but with a lot lesser number of calculations. It saves computation time, it saves computational energy, and it increases the computational efficiency. And as computational energy is saved, in that case, the battery lifetime will be more. So if it's a battery charged device, maybe a sensor node deployed at a jungle, in that case, suppose that thing has to be, that node has to perform, that no microcontroller in that node is supposed to, or DSP processor in that node is supposed to perform a DFT. So more than DFT, it will prepare FFT, an algorithm that has to be embedded in that microcontroller node. More than DFT, you have to do it FFT, because FFT is a lot less computational, and FFT will be saving a lot of computational energy. That will save the battery power, and that battery power saving will increase the network lifetime. Okay, so all these things are interrelated. FFT has, so how many, what is the rule of DFT? So it is n square multiplication and n into n minus 1 addition. But FFT has n by 2 log n base 2. How to calculate log n base 2? It is log n by log 2. Base you can take 10, base you can take e, it doesn't matter. Okay, but log n base 2 is nothing but log n by log 2. So FFT has n by 2 log n base 2 number of multiplication, and FFT has n log n base 2 number of multiplication. Sorry, one should be addition and one should be multiplication. So we will see, and we'll find out which one is the addition formula and which one is the multiplication formula. So here it is given 8-point DFT uses 64 multiplication and 56 addition. Okay, and 8-point FFT uses 12 multiplication and 24 addition. So this n log n base 2, this is actually addition, and n by 2 log n base 2 is number of multiplication. So for DFT, multiplication was more, addition was less. For FFT, multiplication is less and addition is more. But for 8-point or 10-point or 16-point, you won't feel the difference. Let us see. Calculate for 64-point. Okay, you are not calculating any 64-point DFT, but if it is 64-point DFT, then how many multiplications will be required? So it is 64 into 64, 4096. And how many addition? 64 into 63, that is 4032. But for FFT, as far as the formula is concerned, multiplication is n by 2 log n base 2. If you do this, calculation will be 192. So just imagine, for DFT it was requiring 4096 multiplication. For FFT, the same result is obtained with 192 multiplication only. For DFT, number of additions were 4032. Uh, for FFT, number of calculations will be, or number of additions will be 64 into log 64 by 2. Okay, so here also there is correction. This should be FFT. Okay, so 384. So for DFT it was 4032 addition. For FFT it is 384 addition. There is something called as computational efficiency. So you can calculate. How to calculate computational efficiency for multiplication? 4096 minus 192 divided by 4096. So 4096 minus 192 divided by 4096 into 100%. So it is 95.91% reduction in multiplication in case of FFT. So previously we found DFT is using 4096 multiplication. FFT is giving the same result with 192 multiplication. DFT was giving result with 4032 addition. FFT is giving result with 384 addition. So how much is saved? So 4032 minus 384 is amount of saving in addition. 4096 minus 192 is amount of saving in multiplication. And if you just put it in percentage format, you are finding that 95.3% multiplication energy or multiplication number is saved in FFT compared to DFT. In the same way, calculation shows that 90.47% of addition energy is saved in FFT compared to DFT. So just imagine. And more is the number of points. So this 64, if keeps on increasing, 1024, 2048, just calculate. You will find that FFT is doing the same thing, maybe with 2 or 3% multiplication, number of multiplications used compared to DFT. So this result keeps on falling, this percentage keeps on increasing, and this difference, so here it is 4.69% kind of thing. So this value keeps on decreasing as the number of n keep on increasing. So for 64 point, we are finding a reduction is 95.31%. Maybe for 1024 point DFT or FFT, you will be finding this result maybe going to 98% or so. Very easily you can calculate and you can find out. So what is the conclusion? Conclusion from this 64 point DFT, it says that with only 4.69% multiplication and 9.3% addition compared to DFT, okay, FFT is showing exactly the same result. Fft is highly computationally efficient. It has, as n increases, the computational efficiency of Fft further improves compared to DFT. So I have calculated for 64 point. You can calculate for 1024 point, and you'll be finding these values will further reduce. That means as your point of a DFT or FFT is increasing, okay, the computational efficiency of the algorithm is also increasing. So with 1 or 2% multiplication or 3 or 4% addition, FFT is going to give you exactly the same result in frequency domain. So this is an amazing kind of invention which was done by Mr. Cooley and Tukey, and they have got many prizes and many awards because of this. And this is one of the most widely referred technology or most widely referred algorithm across electronics and communication and other branches also. Innumerable applications this thing is having. Okay, and this is the first step. If you just go for image recognition or maybe voice recognition, speech, fingerprint, any kind of recognition, first step is converting the signal from time domain into frequency domain. And to do that, as you are using discrete kind of device, laptop computers, so processing is being done by MATLAB, okay, which is also a kind of discrete kind of a processing every time it is doing. So first step in processing is you have to convert the signal into frequency domain. So this FFT is used for that. So these are basic things taken from Wikipedia. You just can go through. So name of Gilbert Strang is also there. He is the father of the universal father of, you can say, linear algebra. Okay, he has described the FFT as the most important numerical algorithm of our lifetime. So it was included in the top 10 algorithms of 20th century by IEEE magazine Computing and Science. So FFT transforms are widely used for applications in engineering, music, science, mathematics, and too much use it has found recently in mechanical engineering, civil engineering, physics, everywhere. Okay, so the basic ideas were popularized in 1965, but some algorithms had been derived early as 1805 because the basis is Fourier. But recently means in 1965, in 1960s, FFT has come. Okay, because the fundamental of digital was not known initially. So digital thing has come, and after that, all the basic algorithms are being converted to digital. Okay. So otherwise, Fourier transform, Fourier series, all those things were there from the beginning. But digital Fourier transform and then fast Fourier transform, all this thing has come after the digitization. So this is actually the algorithm. This is not required for your exam, but what property they are using for FFT. The symmetric property is being used. When I'm doing some numerical, I will show you when we are doing 8-point FFT, I will show you the periodicity property of Twiddle factor. Here also you can check the periodicity property of Twiddle factor, that you can check this one and this one. Okay, so for these two positions, they are the Twiddle factors are same, but only they are complex conjugate. And this portion and this portion, okay, their Twiddle factor is same, but their amplitude is same, but they are complex conjugate. So if you know only this part, you can write about this, you can write about this, and from this you can write about this one. Okay, so it's that complex conjugate part, that periodicity property and other thing. Okay, it is actually used. So two properties are used of Twiddle factor, and the whole algorithm is actually dividing the input space, whatever is given, into the even part and odd part. So in 4-point FFT, x0, x1, x2, x3 is given. When we are doing DIT FFT, we will find that first we are dividing the input, that is x0 and x2 we are taking one part, and x1 and x3 we are taking another part, and processing the even part and odd part separately. That is one very important thing which is done in this DIT FFT, that is decimation in time FFT. Actually, there are two algorithms. One is DIT FFT, one is DIF FFT. So decimation in time and decimation in frequency. In your syllabus, DIT FFT is there. There is no mention of DIF FFT in your syllabus. Okay. So both these things are using this property of symmetry and periodicity of the Twiddle factor. So it's all a Twiddle factor based game. So splitting the DFT into two parts. Okay. So one is the even part and another is the odd part, and manipulating the Twiddle factor. So as they are complex conjugates, then manipulation becomes easy. Okay. So this is the fast Fourier transform formula. So this is the first part is the even part, second part is the odd part. Okay. So FFT complexity reduction, how it is done. So this is just I'm giving you for knowing. It is not for understanding, or you won't have to go through the derivation in detail. Though derivations are not very big for electronics and electronics telecom, students are writing all this derivations in exam. Not very difficult, but you only understand how to do it. Okay, so here this multiplication and reduction is happening like this. So here one very small account is given, that is for 8-point FFT. We are having 36 multiplication, and we are saving actually 28 multiplications. So 8-point FFT, I doubt. Okay, this is for half actually, they are calculated. So these are two types of FFT, DIT FFT, DIF FFT. For your case, only DIT FFT is there. Okay. So there is a proof, DIT FFT proof. Again, the same thing. It is divided into even part and odd part. It is not there in your syllabus. Just any interested student, you just can go through. Not required. Okay. So what we'll do today is we'll just do the one thing that is called as butterfly structure for 2-point FFT first. So what is meant by FFT? And FFT is nothing but fast Fourier transform algorithm. Result is same as DFT, but is done in a different way. The algorithm is little different. So if I give you one sequence, that is x0 and x1 in time domain, discrete time domain, how to find capital X0? So I asked you to find out 2-point FFT. Okay. So how to find capital X0? So 2-point FFT means only x0 and x1 will come. That is capital X0 and capital X1, which is called capital X at k is equal to 0. That is x0. That is nothing but addition of two sequence. So if I give you find 2-point FFT for x and 2 and 1. So while calculating x0, so x0 is nothing but 2 plus 1 is equal to 3, and x1 is nothing but 2 minus 1 is equal to 1. That's all. Okay, and there is no j part, there is no complex conjugate, there is no frequency of complex frequency thing. Okay, so it is x0 and x1, that is 2 plus 3 and 2 minus 1. That's all. This is the 2-point DFT. 3-point, 6-point, 12-point, 15-point DFT, FFT, all can be calculated. So there is called as split radix DFT. So like you are doing 4-point DFT, 4-point DFT is a radix 2 DFT, where it is 2 raised to 2. 8-point DFT is a radix 2 DFT, 2 raised to 3. 16-point DFT is a, FFT is a radix 2 DFT, that is 2 raised to 4, likewise. Okay. Like 9-point FFT, you can find out 3 square is 9. So in that case, it will be called as radix 3 FFT. Okay. How can you find 6-point FFT? So we know how to find 3-point DFT. We know how to find 2-point DFT. So if you are doing 3 into 2, you are getting 6-point DFT. So whatever signals are given 6-point DFT means we are having xn length as 6. Okay, we will divide them into, so in two ways it can be done in 6-point DFT. Either you divide the inputs into two different categories of 3-point each, or you can divide inputs into three different categories, three different sectors of length 2, and you can do the mix and match. So all these things are there, but for your syllabus it is only radix 2 DFTs or FFTs, so we'll stick to that. Okay. So FFT computation, butterfly structure. What is meant by butterfly? Now just check. So here this is called as the butterfly structure. So this is the basic structure of FFT. So there's an input x0 I have written as 2, and this is x1 I have written as 1 because I have given you the input as, so this numerical I have shown mathematically, and this mathematical algorithm you have to draw in case of exam. Okay, so there's a butterfly structure. So first this thing goes here, okay, and from below this thing goes here. So this is 2 and this is 1. So this x0 is 2 plus 1 is equal to 3. Okay. And this 2 comes below, and this 1 goes through here with a minus 1. So this is actually the algorithm, part of the algorithm. So it comes here. So this 1 becomes minus 1. So 2 comes from top and 1 becomes minus 1. So x1 is 2 minus 1 is equal to 1. Okay. And this looks like a butterfly. That's why it is called butterfly structure. So if any two things are given, real things, there is no j or anything. So 2 and 1 given. So x0 will be 2 plus 1, x1 will be 2 minus 1. So this is how 2-point FFT is calculated. This is how 4-point FFT is calculated, and we'll do this. We'll do one numerical and stop this session. So what we have done is, so given is x0, x1, x2, x3. The same numerical we have solved for DFT, we will solve by FFT. So x0 and x2 is grouped. This is called as even part. Okay, and x1 and x3 is grouped. That is called as odd part. So I had given you 2, 2, 1, 3. Okay, so 2 and 2 was so 2, 2, 1. So this will be 2 and 1. X0 was 2 and x2 was 1. Okay, and x1 was 2 and 3. So this will be 2, 1, 2, 3. Likewise. Okay, and just check the algorithm how it happens. It's exactly the same thing. This is called DIT FFT algorithm, and you have to draw the same thing and execute, and here we are going to get all the results. Okay. So first x0 will come and then x2 will come. Okay, so you have to rearrange. So this is called bit reversal. So input has to be rearranged in case of DIT FFT. So x0 and x2 and x1 and x3. So x0 is here and it comes below, and x2 goes up. So w40 is 1, w40 is 1. You won't have to think. W40 is 1. Okay, these are two little factors you have to remember, and w41 is minus j. This is the only thing you have to be careful in case of 4-point FFT. That is w41 is minus j. Okay, now how to find this thing? We are going to see in the numerical. So given us 2, 2, 3, 1. So first thing we have to divide this into a real part and imaginary part, even part and odd part. Okay, so 2 and 3. So 2 and 3 are the even part. So x0 is 2, x2 is 3. We have written this, and then 2 and 1. So this is 2 and 1. So this 3 goes up, okay, and 2 comes here. So at this point, so first point, this thing is 2 plus 3. So 2 comes from below, 3 comes from below, and 2 comes from top. This thing is 5. Okay. And next, even 2. So x0 is 2 and x2 is 3, and there is a minus 1 here. Don't mistake this minus 1. There are 4 minus 1 in this algorithm, here, 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 and here. Okay, you should not mistake this. There are 4 minus 1 in this algorithm. Okay, so this is x0 and x2. So this thing goes up 3 into 2. So there is no minus here. So 3 plus 2 is 5, and here the 2 comes, and 3 into minus 1, so 2 minus 3 is minus 1. So this is the stage 1 output. Same here, 2 plus 1 is equal to 3, and this is 1 minus 2, or 2 minus 1, this is equal to 1. Okay, so here comes 1 gets multiplied with minus 1, so this is minus 1, and from top comes 2, so this is, at this point it is 2 minus 1, that is equal to 1. And this 1 again goes up, this 1 again goes up, and this is producing 1 again goes up, and this is actually producing 1, and this 2 comes from here, this is 2, so 2 plus 3 is 2 plus 1 is equal to 3, likewise. So first stage output is 5 minus 1, 3 and 1. Okay, this is before multiplying it with the total factor, and there is no total factor here in these two places. What next is, this 5 comes here, so now you have to write input for the second stage. So 5 here, no total factor, it is 5. Minus 1 here, no total factor, minus 1. 3 here, multiplied with total factor w4 0, that is 1, so again 3. And this 1 multiplied with total factor minus 1, that is minus j. Okay, so this step is important, and main mistake happens at this stage. So 5 comes 5, minus 1 comes minus 1, 3 comes 3, and this 1 actually is multiplied by this minus j. So there is only one change in the this and this point, that is minus j. Now again you have to follow the arrow. Okay, so what is the first line? First line is 5 comes here. Okay, 5 comes here, and from below 3. Okay, so this structure you have to practice, and it is very symmetrical in nature, and you have to understand that logic, and it can happen very easily. So 3 comes from below, 5 here, so 5 plus 3 is equal to 8, that is x0. You have already calculated it, you can confirm. So x0 is equal to 8. Then comes x1, so this is actually the first thing, minus 1, it comes from here, and this minus j comes here. Okay, so this is minus 1 minus j, likewise. Then there is this thing coming below, so this is the bottom half. So this was x0 and x1 was the top half, which is actually produced by the even part, in the bottom part which is produced by the odd part of the input. Okay, so this 5 is coming below, and it is actually added with this one. Okay, 3. So this is 3, and 3 is getting multiplied with minus 1. Please don't forget this minus 1. So this is 5 minus 3, that is equal to 2. And next is this minus 1 is coming, and this is also minus j. So minus j and minus 1 is plus j, and from top it is coming to be minus 1. Okay, so this will be minus 1 plus j. So this is minus 1 coming from top, and this minus j and minus 1 is plus j, so this is minus 1 plus j. So this is how the 4-point DIT FFT algorithm works. Same numerical, 1 or 2. Okay, I have given you a 2-point input, and I am asking you to calculate 4-point DFT. How is it possible? So first what you have to do is you have to do zero padding. Okay, you have to do zero padding, and it will become 1 2 0 0, and then separate the even part and odd part. So even part will be x0 1 and 0, so this is 1 and 0, like this. So this is x0 and x2, and bottom part will be 2 and 0, so bottom part is 2 and 0.